Hello everyone. So after discussing different approaches and the value of immunophenotyping in plasma cell neoplasm as well as minimal residual disease, we have also gone through the live analysis, live processing, acquisition of plasma cell samples and MRD samples today. So now this is time to go through the live analysis of few of the cases, and I am Dr. Prashant Timbare from Tata Memorial Center, where I will take you through the live approach to the analysis in multiple myeloma or plasma cell neoplasm through couple of live cases analysis. And before going to that, let's revise few points which is useful for the live analysis. So we identify plasma cell. Traditionally, we are using CD138 and CD38. You can see here the CD38 and 138. So plasma cells are nicely, brightly expressed by using CD138 and CD38. Although all these markers have limitation that we can discuss later on. Then we also have to know what is the expression pattern of normal plasma cells and abnormal plasma cells so that we can identify plasma cells and then we differentiate between clonal abnormal plasma cells from normal plasma cells. So if you see as I've shown in earlier slide, we use a specific marker for the gating. So first to identify plasma cell we use CD138, 38, and in nowadays we are also using CD229, CD319 for the identifying the plasma cells, especially in patients who has receiving anti-CD38 therapy. Then we have markers which are expressed in plasma cells like CD19, CD27, CD81. So CD19 is usually moderate to weak, shows moderate to weak expression in plasma cells. Plasma cells are strongly positive for CD27 normally, and they also strongly show strong expression of CD81. They are polyclonal in nature, and they show moderate expression of CD45. So we have to know that the normal plasma cell shows moderate expression of CD45. Now, if you look at in contrast to that, if you look at the neoplastic clonal plasma cells, so aberrant expression, they show some aberrant expression like CD20, CD56, CD28, CD117, CD200. So these markers are not usually expressed, or these markers are taken traditionally as the abnormal expression in plasma cells, indicating those plasma cells are malignant or neoplastic plasma cells. Although there is some limitation to that, which we'll discuss later. Then that is one aberrancy. The second aberrancy is loss of antigen which are normally expressed. So as I mentioned, normally they express CD19, 27, CD81, CD45. So in abnormal plasma cell, they usually lose these markers. Like CD19 is lost in majority of the patient samples. CD27 is also CD45 and CD81. And of course, those plasma cells are clonal, so they shows intracellular light chain restriction. They express either kappa or lambda. So this is just to show you these are how these normal plasma cells looks. We have seen these plasma cells indicated by purple color. You can see they are gated by using CD38 and 138. So 38 is brightly expressed, almost half log above rest of the cells, and CD138 also more than 1 log above rest of the cells. Now you can see here the CD19 expression. The CD19 expression is usually based on the flowcom, they are moderate to dim. Usually they shows weaker expression as compared to the normal lymphocytes. They have moderate expression of CD45, and these the greenish yellowish color cells are basically hematogones, and the blue cells are B cells. So these are mature B cell, hematogones, and plasma cells. So you can see the plasma cells are brighter than hematogones for CD38 expression. You can see here CD45, the hematogones are weaker and plasma cells are also weaker, but normal B cells have shown strong expression of CD45. The same way, if you look at CD27, it is brightly expressed in plasma cells, and CD81 is also moderately expressed in plasma cells. These are basically the cells which shows bright expression of CD81 are hematogones. So these are the normal expression patterns, and we have to know normal expression pattern because in clonal plasma cells these expression patterns are altered. So if you look at the frequency wise expression of these markers in normal plasma cells, CD38 138 is considered 100%. Although this 100%, but CD138 has limitation because CD138 is very labile kind of protein, and it can be lost uh, after exposure to the cold or transport, and may not give 100%. It may not identify 100% plasma cells. That is our usual experience. So especially in transported sample. So that's why you have to use a combination of CD138, 38, and 45 to identify plasma cells. And how we will discuss in the live analysis. Then if you look at in 97, more than 97% of plasma cells are CD19 positive, which indicates that up to 30% of plasma cells, normal plasma cells, can be 19 negative. So not all CD19 negative plasma cells are always abnormal plasma cells. Then we have CD27 is normal plasma cells express 100% cases. Of course, more than 85% of plasma cells are usually negative for CD56. But you have to also note that up to 15% of plasma cells can be positive for CD56 expression. But most important part is this CD56 expression is usually weak or dim. Then again, CD20 is not expressed in plasma cells. CD117 is usually not expressed in plasma cells. CD28 also not expressed in plasma cells. Normal plasma cells shows 81 bright expression. Again, its weights also show some variability. You can have up to 15 to 20% plasma cells which can be 81 negative. CD200 can be variably expressed, so only bright expression to CD200. Homogeneous bright expression can be taken as clonal. And these plasma cells are polyclonal. Now, if you look at the abnormal plasma cells, as per the literature, usually the CD45 is deemed to negative, that is lost in abnormal plasma cells. More than 95% of cases shows the loss of CD19. So this is pretty reliable marker because loss. It is very sensitive marker but not specific because in 30% cases or 30% cells we can see loss of CD19. Then again approximately half of the cases shows down regulation of CD27. In approximately two-thirds, that is 75% cases show aberrant expression of CD56, which is important. That is why it is very important marker. CD20 is expressed as per the literature in 30% of myeloma, but in our personal experience, it is a very small number of myeloma shows CD20 positivity. CD117 expressed in 30%, CD28 from 15 to 45%, and a loss of CD81 can be noted in up to 70% of cases. And bright homogeneous expression of CD200 can be used also as an abnormal marker. So these are the percentage, and these percentage are important when you are coining or you are designing your panel, which indicates that you have to have these markers. The only liberty you can take in these markers is last four markers, but any myeloma person, any case, any laboratory which is processing multiple myeloma must have all first six markers in their panel. This is our data when we look at which in 219 cases we looked at what is the expression pattern of these different markers for the utilization. So we have noted in loss of CD19 in 98% of cases, followed by loss of CD81 in 95% of cases. So we thought these both markers are very important. Then CD56 was aberrantly positive in 76% of cases, and CD27 was also frequently down-regulated in almost 80% of cases, which is very important. So it indicates that, followed by CD45. So it indicates that in our data we noted that CD45, CD19, CD56, CD27, and CD81, the very good markers for the identifying abnormal plasma cells. And then in one third cases, the CD20, 117, and 28 were also helpful. Now you have to also see that CD38 can be down regulated in approximately one third of cases. uh, Not complete negative, but it can, like, it usually it is bright, but it can become weak or moderate in expression. Most of the cases moderate in expression, or slightly dimmer than normal plasma cells in one third of the cases. So that slight dimmer expression of CD38 cannot be helpful in the this one cases. And we also evaluated series 200, 44, and 49D, but we did not find that much helpful, although 200 was useful. Now, why do you need so many markers? The reason we need so many markers, because, as I mentioned, CD19, which we use as a aberrant marker, is CD19 loss. Normal plasma cells also can be up to 50% of normal plasma cells can show down regulation of CD19. So CD19 down regulation does not always mean abnormal plasma cell, and up to 25% of plasma cells can show CD56 expression. So all CD56 positivity does not mean always abnormality. And even CD45 down regulation can also be seen in normal plasma cells, the same with CD81. So these markers, and that's why we need the combination of these markers along with light chain restriction. So personally, I like to perform light chain evaluation in all cases to confirm the clonality of those plasma cells, which looks like abnormal based on the different markers. And so that is why you need the markers like 319, 45, 56, 38, 138. Along with that, we also need CD27, CD81, and if you have 28 and 117, that is very, very good. But I think the light chains, according to me, are very, very important for the plasma cell neoplasms. And just to show you how the normal plasma cells, what type of abnormal expression normal plasma cells can also show, you can see CD45 can be downregulated in 50% of normal plasma cells in 50% samples. And this was data from 41 normal plasma cell samples. We have also noted in 46% of cases loss of CD19 in variable plasma cell population. We have seen in 10% cases 56 expression, and even we have noted loss of slight down regulation of 27 and 81, also up to approximately 20 to 25% cases. And that is why these markers are not enough, and you have to use light chain expression for the confirmation of the data, unless proved otherwise. So useful markers in multiple myeloma. If you look at the sensitivity, these are the markers we find very useful, like CD45, 20, 19, 38, 56. 38, when I say 56, 38 means weak 38. CD117, CD28, and CD27. And if when we look at other markers like recently used, the CD81 was pretty helpful. CD200 was also found pretty helpful. But the other markers like 44 and 44 and 49D were not helpful. Just to show you, this is an example of null problems. Anyway, we were going to discuss in cases, so I will discuss this part in the cases. And if you want to look at the literature, so this is old paper. So in 2017, my colleague, our team has published one review article. So you can go through that article to look at what are the different applications and what is the clinical relevance of immunophenotyping in plasma cell disorder. Now we'll move to the live analysis. So bear with me. Okay, so let's start with the first case. These are the basic plots we have. I'm not going to the history because we'll discuss the analysis part unbiasedly. So what we these are the basic plots where we see the time plot, as everybody knows, to see the acquisition was smooth or not, whether any bubbles or anything wrong with the acquisition. And you can see here in the upper part of acquisition there are very few cells, indicating that the cells were over in this acquisition, and only small air has been acquired at at the end for few seconds, showing the just background noise. So we can exclude that noise by using time gate. Here we use time gate, we can label it time. We don't need color for it, so that's our time gate. And then we have forward scatter gate for the singlet analysis. We can look at this gate. You can see there are doublets here and some debris here, so we can start with singlet gate first, so remove these doublets. In diagnostic cases you can remove the doublets, but in MRD cases possibly we may want to include just to avoid the loss of hyperdeployed plasma cells. So this is our singlet gate. I'll just increase the size of gate so that everybody can see here. So time gate, singlet gate, and this is viability gate. Viable side scatter versus, so we can see there's few debris here and the rest of the cells, so we can apply forward scatter, side scatter base gate, where we can exclude the cells which are very small by using viability gate. So we can label it SS versus FS viability gate. One thing I mentioned to forget is we have applied time gate here, but we have to apply singlet gate here, so that we'll get rid of most of the doublets. And here we got rid of or possibly non-viable cells. And then we have our usual plot, side scatter versus 45. Some people prefer this, or some people are used to the other way around, that is 45 on x-axis. So this is the thing. We can apply viability gate here so that we don't have non-viable cells in our gate. So this is our viability gate. These are viable cells. Now this plot just to give us the idea what was the processing, how many granulocytes, whether due to processing we lost some granulocytes. It looks like during processing we have lost some side scatter, possibly this was transported sample. Anyways, I've taken this random sample so that we know that we can deal with the issues which can be faced at any random sample. So we have this sample where the sample was sent to us for the diagnosis of plasma cell neoplasm. So we'll start with the first. We know, as we have mentioned, we identify plasma cells by using CD38-138 expression pattern. So let's see, let's start with that. So we start with CD38 and 138 here. So it looks like we have some events which are both CD38 and 138 positive here, a lot of cells, and adjust some scale so that we will have a nice uniform time cluster. Okay, now sometimes we can have some cells. You can see there are cells which can be negative for little bit expression of CD138. So you can see although the most majority of 138 positive, but there are few cells which are going down towards. So the other plot we prefer is CD38 and CD45 like that. Okay, now we have two plots here, and we have to use a combination of these three markers to gate the plasma cells. And how do we do that is to first, as I mentioned, sometimes CD38 can be lost, so we'll start little CD38, but in abnormal plasma cells. But in abnormal plasma cells, even CD45 is lost, so generally it is safer to take a little deeper on this side. So we always include CD38 dimmer population in CD45 negative, because if you have CD45 negative, CD38 dim, most there are very high chances those cells are basically plasma cells. And then we also apply another gate at CD138 and 38. So you can see they are bright, so we can always go up to here. And I usually extend this gate till negative so that we can include all possible plasma cells if they are there. You can see here, just based on these two gates, possibly we are excluding some of the cells from the analysis. So yeah, so we can label this gate as series 38 versus 45, and before putting this gate you can, so before putting this gate, you see that we have included all the cells which were positive in this gate, right? Let's check out that. So we have given one color to this and we have included all the cells here, so we are not losing here. In fact, in this gate there were few cells which were not included, so which we have included in this gate, and which we level at cd 138 versus cd 38 gate, level like that. Or, and then once we know that we are not losing any cells because of CD130 and 38, we know that this gates looks better in combination, which include all these plasma cells. So between these two we can finalize one gate, and what we can do is if this gate include more events, then we can apply this gate on the top of CD138 38 gate and include those plasma cells. Or if our CD138 and 38 looks more compressive, then we can put this gate over CD38 and 145 so that we can exclude if there are any debris or CD45 positive cells from this gate. So we can put like CD138 and 38 here, and we can see there are few cells which are doublets which we can exclude by using this gate. So this would be our final plasma cell gate. This is how we can look for the plasma cells. Now we know that we have applied both 138, 38 and 45 and excluded junk from this gate. So that is another advantage, that we can exclude the junk, we can include so on this. So this is a gating, this is how we do the gating of non plasma cells, these plasma cells. Now once we know that these are the plasma cells, this one, then we can label it like this final CD38 versus 138. It's a good idea to have these plots, two plots like that, just for the review. I'll keep it here. Since this was our, yeah. So because we have combined both the approaches to include all these cells, we can label it final plasma cell gate. Right, so we have this final plasma cell gate, and if you want to look at the percentage of these plasma cells, means we can look at here also, because these are pretty much represented, or you can look at the number of events divided by the total events. So just for the to save the time, I can show you here number of, these are approximately 2.35% of plasma cells we have here in this sample. Now, once we identify the plasma cell, the next thing is to look at a different expression pattern to identify if they are normal or abnormal, and if they are abnormal normal, then what is the percentage of normal or abnormal. Right. So let's take this plot and copy paste it here now, and check for the common markers like 19 and 45. So yeah. So do we see any plasma cells? So I see the most of the plasma cells are CD45 positive. However, the CD19, it looks in majority population moderate to dim, but there are few cells which are here and which are here. So which possibly these cells are basically 19 negative, and these cells are 45 negative. So we have these two populations here. Well, let's see for the other abnormalities first. So we can get this population as a CD19 positive but 45 negative. We can label this population as 45 positive but 19 negative. Okay, so we have these two populations. Then we can look for 19 versus 56, and we have 56 positive population, isn't it? So can put a gate here to identify the 19 positive, 56 positive population here. Okay, we have to put final PC gate on this. Yeah. And there are few cells which are maybe 56 positive here and 19 negative. Let's give it a different color, maybe red. So we can call 19 negative and 56 positive. and these were 19 positive and 56 positive. Okay, so now we have different combinations. So we have looked at 1945, 1956. One more marker which is usually used is to look at CD27, and we can look at the CD27 along with 19 as well as 56. So you can see the 19, the cells which are 56 positive shows moderate expression of 27, which is kind of more or less normal. And we have again 56 positive here, and then 27 deemed to negative population here, which is 56 negative. So we can get this population like 27 positive or 27 negative population. Can say 27 negative PCs, and we can also label 27 negative only 56 positive PCs, right? So 27 negative and 56 positive PCs. So these are the different type of cells which can have abnormal expression, because we have seen CD27 and 56 positive 27 loss is abnormal, 19 negative 56 positive abnormal, 27 can be lost in abnormal. So these are the population. Now these are the population, but are these abnormal? Because they do not show the very synchronous cluster of abnormality or clear cut means abnormalities of multiple antigens where you can identify plasma cells. Majority of plasma cells in this case, in fact, shows normal expression of 45, 19, 56, 27, right? Now, only way to confirm is to look at the light chain expression of this. Otherwise, one can always call these plasma cells abnormal or these plasma cells abnormal, just without, if we do not use any light chain restriction. So that is why it is very important to use light chain restriction to confirm, especially in cases where the plasma cells are not many or the diagnosis is not confirmed. Confirm means there are no other evidences of plasma cell neoplasm like lytic lesions, M protein, and so on. So next a thing is to look at light chain expression. So we have kappa here and lambda here. So you can see there are two clusters of kappa and lambda here. The one which is kappa and the other one is lambda. You can always adjust the scale so that it will looks more real. Uh, See, yeah, the light chain expression in myeloma, they have very strongly expressed. So you have to be very careful when you are interpreting the data or the put analysis. So you have to adjust in a such a way that you can get this. So if you look at all plasma cells, they looks pretty polyclonal. Just to confirm their percentages of kappa and lambda, let's see. These are kappa positive. This is, and if you look at their percentage was 64. These are lambda positive disease, and their percentage is 32, so which looks pretty normal. Right. So we have both kappa and NAD. In fact, in this possibly the light chain, we have put more amount of antibody. That's why it's pretty bright. So we have to tighten it down in such cases. If you have less number of plasma cells and if you put higher amount of antibody, it can show very bright expression. So little bit tighter down is helpful. Anyways, but still we can see there are different two clusters of plasma cells. One is kappa and then which looks pretty polygonal. Now we have to look for the different gates, the different suspicious populations, whether any population out of them has any clonality, evidence of clonality. So let's start with that. So let's start with the gate with 19 negative, 19 positive and 45 negative. They looks polygonal. Then then we have 19 positive, 45 positive. They looks polygonal. Okay, we have to wait to program. I have given command, so sometimes the software doesn't like when you give many commands unless you have very good workstation. So let's wait for a few seconds. Yeah, accepted our request. Let's copy it down, paste, and then we can try other. Okay, we had 19 negative, 45 negative. Okay, they also look pretty polygonal. I'm going to change the gates on this now instead of making new plots. So 19 negative, 45 negative population which we have seen, it looks also polygonal. So that is the point I'm going to make. So not only the loss of markers does not mean they are abnormal clonal plasma cells, they can be normal polyclonal plasma cells. Then if you look at 19 negative, 1956 positive, in fact those are also pretty polyclonal. You can see the 73 to 25, they are not clonal. So even 56 expression and 19 down regulations means the combination of two abnormalities also is not helpful for identifying plasma abnormal plasma cells. And then we had okay, 19 negative we have seen that. Then let's look at 27 negative, 56 positive. So in fact those are also polyclonal. So even 27 negative population also is not helpful. 56 positive population, so loss of 27 can be also seen in polyclonal plasma cell. Only 27 negative plasma cells where we have seen those are also polyclonal. What else? Then 45 positive, 19 negative, those are also polyclonal. And then we had looked at, okay, so all possible combinations we had looked at. So you can see here, okay, we can also look at 20 expression because we have not seen 20 expressions. So let's see if we have any plasma cells which are 20 positive, and we don't have any 20 positive blood. There are few non-specific binding cells which are 19 and 20 positive. So otherwise there is no 920 positive cells, and this is just an autoflow. Because of autofluorescence there is higher background in plasma cells which is coming up to here, but they are not truly positive. We can always adjust that to like this and adjust the scale in a such a way that it will more be representative like this. Yeah. So there are no 20 positive plasma cells here. There are a few events here. Let's check those events too. J, and let's try that. It looks like there are a few doublets which are coming here, which are going for both kappa and lambda here. You can check with other marker. Let's see, 45. And there are no events here, so you can see these are the 20 positive events which are actually pretty polyclonal. With 56, yeah. So here you can see they are pretty polygonal. So with 19 and 20 there were some doublets which were coming here, which were coming both 19 and 20 both positive. This was 56 were polygon. So basically all plasma cells polygonal. So this is just a case which was we were evaluated for different markers. These were not basically submitted for the plasma cell neoplasm, but this was a case of staging myeloma, and because there were increased plasma cells, staging case of solid tumors uh, in a pediatric patient in child, and we were evaluating a normal expression of plasma cells, so that's where we're looking at the normal expression. So you can see this normal expression can be shown in different way in plasma cells as compared to the, and that is why it is very important to look at all markers in combination with light chain. So the other question will arise, why don't use then light chain? So if you have 90% plasma cells, why not? We can use light chain and very few. So that's what people have done when they're using 3 or 4 color. But when you are monitoring the plasma cells, then it is very important myeloma in a cases where the plasma cells are low in number, and you may have less number of clonal plasma cells in the background of other normal plasma cells. Then we need different markers to identify those plasma cells and then look for their clonality, and that is why we need the combination of these markers. So this was a case of normal plasma cells. We'll discuss the case of myeloma as well as MRD in next few minutes. So if you have any question, maybe we can discuss those questions for 5 minutes with 5 minute break. I would request Khalid to take few questions for during this time, and then we can again, if we do not have questions, then we can start with the analysis, or we can do the analysis of both first, complete analysis, and then we can take a question. So we can decide that. Okay.